if this is working. It is working. Cool. Hello. So let's go to our first note set. We have our exam next week. This will be on note set 7 through 11 with extra credit from note set 12, which will start on Tuesday. So today what I'm going to do is at least start by reminding you of things in the note sets. We can talk about problems. We can do whatever you want. But I just want to remind you of things that are important to study. I'll also let you know things that you don't need to study as we go through the note sets, because there's some derivations in there that I will not test you on at all because they're just too ridiculous. So we're going to start with harmonic excitation of undamped systems. Basically, this whole test is on force vibration, where you have some force acting on a system that will cause some sort of steady state response because of that force is present. And we're going to look to see how the inclusion of that force impacts the response of the mass. So the big thing that changes here is that we had this additional force F of t that is driving the system. Now we'll discuss more in detail, but what we see is that this force doesn't just depend on how big it is, it also depends at what frequency it's driving the system at. So for this, the frequency, which we call omega, drives the system. So that's an external type of force. Again, that can be the motor of something or the road or whatever it is, that's external. While the natural frequency is just based on the stiffness and the mass of the system, right? Two different frequencies. That's the big moral here, because we know that omega n is the square root of k over m, while the omega is dependent on the external stuff. Is that okay? So we first started talking about what happens when a force is harmonic, meaning it's sinusoidal in nature. It's oscillatory. It could be cosine or sine, but it oscillates. So basically this force as a function of time might look something like this. Or if it's cosine, it might look something like this. All that changes is really a phase difference between the two inputs. But we see in this expression that the force that's acting depends on some amplitude. Remember, the term that's in front of the sine or cosine in any situation is the amplitude, because sine and cosine vary between -1 and 1. So the amplitude is associated with the max of the system. So if cosine is 1, that means the max force is F naught. That's the amplitude by definition. Because some people were confused the other day. What do I do with this sine? It's like, well, we're looking for the amplitude. So the sine term doesn't even matter, the sine of omega t. But we're just looking for amplitude. It's just the coefficient in the front. So we derived this differential equation, and we see that it's the same form. This is without a damper, but it's the same form compared to every differential equation we've done in this class. The only difference is we now have this forcing function on the right. That's associated with what from a differential equations perspective? The particular solution, right? So now we will have also some x of p because of the fact that we have a driving force. Is that okay? And just like we did earlier in the class, when we divide by the mass, we convert it to this monic form relationship, where we define F naught over m as what we call little f naught. There's a lot of equations that we'll see that depend on little f naught. It's just a normalized force where you're dividing by the mass. And that's what the little f naught represents. So in regard to the total solution to the differential equation, we add the homogeneous and we add the particular together, where the homogeneous is what we derived in the earlier note sets. That was when we assumed the solution for x of t. We saw that there were three ways to represent that. You can represent that like I have on the board here, where you have the sum of a cosine wave and a sine wave with different amplitudes. What are some other ways we can represent it? An exponential, we can do an exponential, e to the lambda t, and we can solve for lambdas. And then what's the third one? Not well plot. So how do you represent x of t, the homogeneous? Yes, you have a sine wave with a different amplitude and a phase shift, and they're all related. So just to summarize that, you could do a sine omega n t plus phi, and you can also do a e to the lambda t. They all end up being related in some way. That sound like review? Is that okay? Again, that's your homogeneous stuff. But I wrote it in this example as the sum of A1 cosine plus A2 sine. And that's based on the natural frequency of the system. Why do you think there's no driving frequency there? No omega? Yeah, because it's homogeneous. The forcing function is 0. So there's no omega at play. It doesn't exist when we're doing the homogeneous solution. So the sum of those two is what gives us the total solution. So the first goal is to try to figure out what that is, and we introduce this particular solution that's in the form of the forcing function. So in this example, the forcing function was f naught cosine omega t. So we said that the particular solution is going to be some amplitude times the same function, cosine, Dylan. Right, because it wouldn't be the same as f naught, because f naught is the system thing. X depends on the stiffness and the mass and all that stuff. So it's not going to be the same variable. We just come up with this arbitrary variable, capital X. That's the amplitude of the system due to the forcing function. So then yes. Yes, exactly. You assume that solution, you'll take derivatives, which is what we do here. And then what we'll do is we'll substitute it in. So you see that we have the second derivative here. That's right here. That's x double dot of p. There is no x dot in this equation. Why not? There's no damper. There's no damper in this node set. This is node set 7. It's an undamped system. But we do have xp of t, which was original x cosine of t. We see that that's here next to the omega n squared. Is that okay? What's nice and simple about this without the damper is that all these cosines can cancel. And then you can solve for x, because if I factor out an x, I'll get negative omega n squared, or omega squared plus omega n squared is f naught. We see that? Factored out the x. Then I can divide by that, and we end up getting our amplitude, where we see that it depends on the force and the frequencies, omega n and omega. Is that okay? Doubts about this concept? So we can add that solution to our total solution. That's the particular. Right, again, this whole thing is the homogeneous. This is the particular. And now to find those unknown amplitudes, A1 and A2, we use the initial conditions. And I go through this math here. You know, you plug in 0 for time. And then when you plug in 0 for time, your output is x naught. You can solve for a coefficient. Dylan. Yes, because at time equals 0, that force is present, right? Depending on if it's sine or cosine, but we're again assuming that that force does have an impact on the initial state of the system. So the total solution is based on both the initial conditions, that's the A1 and A2 stuff, and whatever the force is. That will alter that entire state. Right, unless I ask you. But in general, if I say in an exam, what's the amplitude or what's the solution, you can just use the equation from the formula sheet. But once you go through all that, you end up seeing what these coefficients are. And what we learn is that this term that was originally just multiplied by cosine omega t also is dependent on the natural frequency of the system. It's multiplied by cosine of omega nt, which should make sense. If I have zero initial conditions, meaning that these guys are zero, if I have zero initial conditions, the system property should obviously have an impact on the response. So omega n has to be here somewhere. It is in the amplitude, but it should also be impacting the oscillations in the form of a cosine wave. So that stuff is all there. So that's what we see with zero initial conditions, that we still have that cosine omega nt term that pops out. Is that okay, Peter? Okay. So I give you an example here where we see that in the system we have both things occurring and we have this weirder response where we have the particular solution and the homogeneous solution acting at the same time. So due to those initial conditions, the mass is doing its thing. Due to the forcing function, it's doing its thing. This combining sum of them is what's going to be the motion of the mass, which is what we see in this picture. Is that okay? So do some physical insight. The first thing we note is that if we're just looking at the particular response, and this is the amplitude, we want to investigate how this amplitude changes as a function of frequency, the driving frequency omega. So if we were to first do a little bit of math and write this in terms of a frequency ratio, let me go ahead and find the final equation. Cool. I don't have it here, which is weird. But this would be delta static over 1 minus r squared cosine omega t. You can go through that math. You see some of the algebra we do, we factor out omega n squared because we like to express things in terms of this frequency ratio r, which again is the ratio of the driving frequency omega to the natural frequency of the system. So what we see is that this is the amplitude. I'm going to have to fix this. There's a lot of, like, there's a cosine here, there's no cosine there. I'll fix that later. We see that when r is 0, that means what about the driving force? Dylan. The amplification factor is 1, meaning that the amplification of the mass, the movement of the mass, its amplitude is equal to what? Not the amplitude of the forcing function. So when r equals 1, that means that, or not 1, sorry, when r equals 0, that means that omega equals 0, right? Because r is omega over omega n. So if r is 0, omega is 0. And if our force is F dot cosine omega t, that means that the only thing acting is F naught, some constant. So that constant is going to pull the mass, and that's it. It's just hanging out. And that's equivalent to the static deflection. Because if I have some constant force, that is what it's going to do. It's not moving the force. It's not oscillating. It's just static. The mass is still because of that force. So when r equals 0, we see that our amplitude is equal to the static deflection. Are there doubts about that? Kristen? Okay. Questions? Okay. That's what we see here. When omega is equal to 0, we have a static deflection, which is just based on the ratio of F naught over K. Right? That's what that means physically. So in regards to this relationship, we looked at a few different cases. We first looked at when R was small. If R is small, what is the sign of this? Positive. So R is small. X over delta static is positive. Huh? It's not less than 1 because if you do 1 minus a small r, let's say, this is 1 over 0.9 or something. So the whole amplification factor will be greater than 1. You see that? This is 1 over something small, which leads to a number that's bigger than 1. So we see that our amplification factor is bigger than 1. What does the sign imply? Peter? Well, I wouldn't worry about rights or lefts. It's a little bit different than that. Because remember, it's against the cosine wave. So cosine will change sign. So at some point in time, it'll be to the right, some will be to the left. So what does that imply? Austin, what are you saying? What does the sign of this matter? If I say the amplification factor, it's the phase. So if it's positive, if the amplification factor is positive, the mass and force are in phase. So if I were to draw a graph kind of representing that, let's say here's time versus the force, and this force is a cosine wave. Maybe it looks something like this. Our mass will be moving. Let's call this xp of t. This is just a particular solution. Our mass will be moving at the same frequency in phase with the force, meaning that when the force is high, the mass is high. When the force is low, the mass is low. So we'll see that it'll have a different amplitude based on x, but it'll be directly in phase with it. What is the value of the phase then if they're in phase? 0, right? That makes sense? 0. And we see that here. Here's an example showing that, where they're both going up and down at the same rate, but their amplitudes are different because the force and the x are not going to be the same at a non-zero frequency. Or really, I guess any frequency. It always depends on the static deflection. But we see that they're in phase. Yes. That's for no damping, right? Because what happens as we approach r equals 1? What happens to that amplification? 1 over 1 minus r squared. So if r is approaching 1, it goes to infinity, which is not physically possible in the real world because of damping. Damping exists everywhere, whether in regards to friction or air resistance or something. Yeah, that's why that ends up occurring, that damping. We'll see that in note set 8. But yes, that's what's happening there. Is that okay? Questions about that? The other case is when we're greater than the natural frequency. We'll talk about r equal to 1 in a second. The only difference is now, if I say that my amplification factor is 1 over 1 minus r squared, if r is bigger than 1, think of a huge number, this is going to approach what? Well, negative is true because it's 1 minus a big number. So this will be negative. This will be less than 0. So what's that imply? Well, yeah, it will be a small number eventually. But what's the negative sign imply? It's a phase thing again. Because remember that our particular response is based on x cosine omega t. So if this x, and if you normalize it just for the sake of graphing, but if you multiply by delta static, you would still get an x value. If it's negative, that means that the position will be 180 degrees out of phase compared to the force. So if I draw the same picture where I say, okay, here's the force, what colors did I use before? I used blue. If I look at the force, we'll have the same cosine wave. But now because x is negative, this is t, this is f of t, this is x of t, it will flip it about the x-axis, which is equivalent to 180 degrees phase shift. So it will be something that looks like this. And that occurs if you're past resonance, if you're past r equals 1, because of the fact that your x has a negative value now. That negative sign doesn't mean the amplitude is negative. Amplitude by definition is positive. That negative sign impacts the cosine, which flips it, makes it 180 degrees out of phase. Questions about that? Concerns? So that's the sign. What's the other thing we know about this? When r gets really, really large, this whole number gets really small. That's a dancing thing I did in class. As we're trying to turn back and forth quickly, the mass does not have time to respond. There's not enough time. Because of its inertia, you're trying to cause this thing to go back and forth quickly. It doesn't have time to think. Hey, go left. Okay, I'm moving left. Go right. I'm still moving left. I don't have time to go back. It's the same thing with the weight. If I'm moving my hand fast, the weight's just standing static. It doesn't have time to move. Does that make sense? Doubts about that concept? Okay. So if you look, when you're less than 1, this is the amplification, or this is the frequency ratio in the x-axis and the amplification factor on the y-axis. And again, this is the equation we're plotting. When r approaches 1, this denominator gets smaller. 1 divided by a really, really small number will cause infinity, some infinite value. And that's what we see here, because as we go closer to 1, which is the dashed line, we see that our amplitude grows. Because again, resonance is the mass's happy position. It likes that frequency. So if you're driving it at that frequency, it's all pumped up about it. It's going to start going wild. While on the other side of this r equals 1, what we see is that we will have a large amplitude that's negative, goes towards negative infinity. But as r gets bigger and bigger, we see that this will end up approaching 0. Out of phase, but still approaches 0. Yes. That's it. No. Is that okay? Cool. So I do a proof here, where I think I tell you, like, I give you just the answer about how it changes if your forcing function was sine instead of cosine. It ends up being slightly different. You end up with this extra factor here. I guess last summer I said it will be a homework problem. I think I did assign it last summer. I forgot to assign it this summer. But the general idea is exactly the same, though. You would assume a solution, except instead of doing x cosine, you would do what? X sine. Question. Yes, those are the same thing. Amplification and magnification. Yes. It means that our amplitude in general is x is equal to delta static over 1 minus r squared, right? That is for a very specific mass and spring, right? So if I have a specific delta static with some k, and based on the input force, that's what that is. To just learn the general trends of any system, we divide by delta static and just plot this arbitrary amplification thing versus just r, which shows us the general trends, where as r approaches 1, no matter what the natural frequency is, that's still true, we end up with this large increase. Or when it's going towards a large r, the value goes to 0. It's just a very general way of expressing it. And from a physical perspective, if there's no frequency, we know that the deflection might be 3 meters. If I start oscillating, how much larger than 3 meters is it? That's what that amplification factor is. If it's 6, that means you have an amplification factor of 2. You've doubled it compared to its static state. That makes sense? Cool. So I show you that there's a little bit of a difference between sine and cosine. That ends up being mathematical. I wouldn't stress too much about this, though. I'm going to make that decision now. Don't stress about this. Just the one in terms of sine. I was like debating if I would give you this question, but it's like not worth it. I agree. The next thing we talked about was beating, which occurs when? Peter. Funny. That's violent, man. Lucas. Almost equal each other. This occurs when they're close to each other, but not equal. What do we have when they're equal? Resonance. But when they're close to each other, that's when you have this beating phenomena. Wah, 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 wah. You have this change in volume as a function of time, right? So I go through a little bit of math here. But what we end up seeing, now let me get the response. Sorry, here, we'll just look here. So we have this frequency, which is large or small? Large. Omega plus omega over 2 will be a big number. This is large frequency, which is based on the oscillations of the mass or the envelope of the amplitudes. The oscillations. So if we come down here, we see that this frequency here, or the period there, that's the oscillation. We see that we have a lot of cycles in a second. The red thing in this picture takes 20 seconds to complete. The envelope takes 20 seconds to complete one period. But the oscillations, who knows how many there are there? I'm not going to count them, but there's a lot more of them, the higher frequency. Do we see that? Luca, you see that? Huh? Oh, you're trying to count them? Yeah, there's a lot. So that's the large frequency component. Then you have this guy, which is based on the envelope. This is the low frequency component. Right? Small omega. Omega and minus omega will be tiny, which means you have a very large period. Yes. Yes, this is only specific to beating, this expression. So I have here this omega n minus omega over 2. That is the frequency of this red envelope, of this thing. That is not the same thing as the beating frequency, because what we look at is how many times does a beat occur in a second. What is considered a beat? A beat is considered all this, and then it stops because it restarts itself. We start low volume. I'll use like the sound as an example from that video. A low volume, it's low, it's getting higher, it's getting higher, it's high, it's high, it's high, it's high, it's low, 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 and then it begins again. That's considered one beat. That's a period of the beat. So what we say is that this thing here is the period of the beat because it restarts after that. And that leads to our definition of the beating frequency, which is omega n minus omega. Okay? So if you were to scroll back up, we see that we have that omega n minus omega in the numerator of this expression. It's right here. When you divide it by 2, that causes the envelope to have this larger period. But if you were just looking at the numerator, that's half of that, which is why we consider that one thing the frequency of the beat, because it just starts itself over again. How are we feeling? We okay? Okay. Lastly, at resonance, we're driving at omega is equal to omega n. This isn't valid anymore because this becomes undefined if omega equals omega n, right? That the division is going to be by 0. You can't have that. So we guessed a new particular solution, which was, again, kind of arbitrary, but we have to include this other factor of t here. That's the big difference between this and the other solutions, is that when we're at resonance, we end up with this other particular solution. But it's the same deal. We take derivatives, plug it into the differential equation, and we would end up getting a different value for x. That is just based on one frequency, because omega and omega n are exactly the same. So you could write this as f naught over 2 omega n or f naught over 2 omega. They're equivalent, right? Omega equals omega n in this case, because we're at resonance. So then we do the same exact thing. We see that this is our amplitude of our particular solution. You can see I made a substitution here for omega n because they're equal. Again, not a big deal. Everybody dropping stuff? Like 4 things in a row. So if you go ahead and do your initial conditions thing again, you end up with this response where you have the same initial condition homogeneous solution, but now what we see is that the particular solution is dependent on t, which means that as time goes on, the overall x will get larger, and it increases linearly. We see that in this picture here, that as time goes on, we end up with a much larger amplitude. That is what leads to things breaking when we're operating at resonance. And this is specifically for an undamped system. We've talked about a little bit how at resonance, the damping will prevent it from going towards infinity. That's the benefit of the damper. But in this case, we see it just goes on forever because there's nothing removing the energy. Is that okay? Doubts about this note set? Okay, cool. Note set 8's the same exact thing. The only difference is that we include a damper. So now we have this damper. A student asked me yesterday, is the damper always acting against the motion? And yes, it is, just like the spring. The damper is trying to slow the system down. So if the mass is moving to the right, the damper will be acting to the left. And the spring always likes to be in equilibrium. So if the mass is moving to the right, elongating the spring, it'll force it back to the left. So these always act against the motion. We see that we end up with the same differential equation. The only difference is now that we include this Cx dot. We can convert the monic form, the same thing that we've seen before, same deal. And then in note set 8, in regards to damping, we can have different cases of damping. If it's critically damped or over damped or under damped. Which one is the one that causes oscillations? Under damped. That's correct. When it's under damped, it's able to oscillate. For this class, we're not going to worry about damped or force systems that are critically or over damped because it's not as exciting. When we do under damped, we actually have something that's steady. It'll oscillate forever, or Rather, the force response will be causing an oscillation forever. And the transient will be oscillatory as well, but it will die out, right? Because the damping is going to start to limit that. So if you go back to note set 5, I guess, which is on damped systems, we showed that this is the response of an underdamped free vibration problem. That's a homogeneous solution of the differential equation, where we see again that for the free vibration problem, it might do something like this, where it approaches 0 ultimately. Remember, the envelope of that, the amplitudes follow this exponential pattern. That's because it's multiplied by this. But now we're going to add this particular solution. Does that sound okay? Anybody freaked out? Lucas? So the big difference between the undamped case and the damped case is now we introduce this phase delay. This exists because of the damper. It exists because of the damper. Why do we put a negative there? Why do we assume it's a negative? Dylan. It pushes it to the right. Let me draw a picture to explain that. So if I have my force, let's say my force looks like this. So this is T versus F of T. We will have the same frequency, but because of the damper, the mass is a little slow at responding. So if you were to draw the same picture for the displacement, this will be starting a little bit later. So you have this phase delay. Negative phase implies moving it to the right. So this original cosine wave moved to the right. That's what causes the response. Do we see that? Dylan? Where I just like didn't start it? Yeah, it's hanging. For T at time equals 0, technically it's hanging. It's not doing anything. It's at, I guess, if you want to think, really we look at this in steady state, because if you're doing this total solution, you would have the transient response acting right away, right? That's the first thing. But if we just assume it's steady state and we're looking at time equals 0, you might see this. It will just, and then it will start to move once it happens. But a lot of times we're looking at like way down the line in time, and we'll just see that it is delayed slightly. So what you would see typically drawn is that this will, continue as if it's a normal cosine wave, just shift it to the right. That makes sense? Okay. And I tell you here that the phases are different. We had a phase from free vibration, which is phi. That's what we have up here in this total equation. This is a phi. Well, this particular solution was x cosine omega t minus theta. Different letters representing different things. What does theta physically mean? It's a damper delay, but what does that mean in regards to the force and the mass? They're out of phase, right? It's the delay caused by the damper. That's correct. That is basically saying that when the force is doing something, the mass will be delayed. That's a very physical thing. What about the phi? Remember, that it is a phase. That's right. But what does it mean? And again, it's not really a physical thing. What is the purpose of that phase? No, not that. I wouldn't say that exactly. No. Remember that in math, our standard sine wave is just sine of omega t, right? This phi is just a mathematical thing in reference to that baseline sine wave. And just telling us, compared to some normal sine wave, how much is it shifted to the right or left? And that depends on the initial conditions, right? Positive amplitude versus negative amplitude, it's shifted in a different way. It's a very mathematical thing. It's not really a physical thing. While the second phase, this is a physical thing. This is the phase between the force and the mass. Do we buy that? I can draw a picture real quick just to show that. But if I have your standard sine wave, this is just sine of omega t, a sine of omega nt, let's say. Depending on the initial conditions, this phase might look like, or this graph might look like this, which is still sine of omega nt, but now it's been shifted. Again, it's just in reference to this baseline sine wave. So phi is very mathematical. So phi is mathematical in reference to baseline sine wave, which is that. That's the baseline sine wave. Does that get confusing? Matt, you had this look of skepticism on your face. Okay. Thumbs ups? Thumbs mediums? No thumbs mediums. Does that mean everybody's thumbs down? Okay. So, this proof here, where I end up doing matrices and stuff, you do not need this proof. Ignore this. You don't need this. Don't worry about this. If I ask you to derive anything for this equation, it will be from note set 9, complex response method, Laplace transforms type of thing. It will not be this crazy matrix thing. I didn't do it in class. It's in the notes for your reference. If you want to look, it sucks. We're not going to do it. So all this stuff here with determinants and grossness, don't worry about it. Is that okay? Is that clear? Don't waste your time studying it. Study other things. So once you go through that grossness, now what you see is that the amplitude x now depends on this damper. If zeta is 0, it reduces back to the equation we had at the beginning of class. It's from note set 7. It's f naught over omega n squared minus omega squared. It reduces back to the same exact thing. Dylan. That's from the crappy derivation. Don't worry about that. Yeah, you have these equations on your formula sheet, first off. And you can get these using the other complex response method, with the FRF, magnitude and phase. That's equivalent to this. So we see that zeta is present. So what does that do to the amplitude? Or what does it ensure the amplitude doesn't do? It ensures it doesn't go to infinity. Because even when omega equals omega n, which is resonance, this term goes away because they're equal, but there's still something in the denominator that's non-zero that you're dividing by. It will ensure that you don't blow up. The damping helps minimize the vibrational response of the mass. Do we understand that? Audrey, Delani, Lucas, Thea. I know everybody's names. Diella. Okay. Similarly, there is a phase introduced by the damping. Like we've discussed, it slows the mass down relative to the force. When zeta is 0, what's the phase? 0. That's correct. It's 0. Again, if we go back to note set 7, when there's no damper, all these equations should reduce to those equations. There was no phase present when there was no damper. The mass and the force were perfectly in phase or perfectly 180 degrees out of phase because of the negative sign if we were past resonance. So the damper impacts that. So here's our total solution where we had the underdamped response due to initial conditions. This is what we call the transient, because as time goes on, it'll eventually die out. It doesn't live forever. While this is the steady state, there's no influence of the damper on that. The force is just doing its thing. Yeah, it changes X, but in regards to the oscillations persist as long as the force is there. That makes sense. Doubts about that? Okay. So yeah, the transient and the steady state. We've already defined this before, but if you do a little bit of algebra, we can convert this, which is the amplitude I just showed you. That depends on the damper and the frequencies and stuff, to this. Well, really what you can do, let's look at what omega n squared over F naught is. Right, I'm just going to look at this guy. What's omega n squared? K over M. What's F naught? Big F over M. Those cancel. This is K over F naught. What is that? That's based on the static deflection, right? F is equal to Kx. If I solve for K over F naught, this is 1 over the static deflection. So this thing here is the same thing as the amplification factor, except now it's based on including the damper. That's the only difference. It's the same equation as before. The only difference is now is that we're including this data, this damper. Is that okay? Doubts about this? I will upload this to YouTube now that this is a thing. Thank you, Charbel, for making my YouTube channel. I'm waiting to go viral. When I do, I'll give you some money, like $10 probably. Thank you for making my logo with my favorite color. What was it? I don't even remember the name that I picked out. I just Googled some random bullshit color. Oh, you did it in AI? Wow. I thought you designed that yourself. It took you 2 hours. Thank you. That makes more sense. All right, your commission's dropped and being split with Lucas. So, oh, I did this here. Yeah, so I show this in the notes that it ends up being the same exact thing that we would expect at the amplification factor. Now it just depends on the damping. There's that equation. I give you that on the equation sheet. And here I said, let's look at the case where there's no damping. It reduces back to what we had in note set 7. Thrilling. It's what we expect. So this is something that people didn't remember from last time. So when R equals 1, let's come back to this equation. When R equals 1, meaning we're at resonance, we're driving at the resonance of the system. X over delta static becomes what? This term goes away. Then you have 1 over the square root of that term squared, cancels out. This ends up being 2 zeta, and then r is also 1. So you have this amplitude magnification factor being 1 over 2 zeta. This is what we call the quality factor. This is Q. So if you read papers or something or look in textbooks, they'll sometimes say the quality factor of the system is this. That gives you a feel for how the damping in the system is. Dylan. It's defined when R is equal to 1. Like this equation is only valid when R is equal to 1. Like that's the definition. At resonance, the peak, which is the amplification factor, right? That is going to be based on the quality factor, 1 over 2 zeta. That's the definition. Let's talk a little bit about this here, where I say it's a metric describing how much energy is lost based on the initial energy stored in the system. So basically you have, I don't even want to go into detail with the periods and stuff, but the moral of the story is that if I have 1 over 2 zeta, if Q is high, what is zeta? Low. If Q is low, zeta has to be high. Is that okay? So if you're looking like at this graph, for example, we can ignore this box for a second. Reminder that Q is equal to 1 over 2 zeta. Which graph has the highest Q? The 0.05 one, this one. The largest peak is related to the largest Q. Big peak, big Q. Big peak, big Q. While these down here have a very low Q because there's a lot of damping. Again, you can tell how much damping there is just basically on how high the amplitude goes. It goes high because nothing's removing the energy, or something's removing not a lot of energy. That makes sense. Perfect. I do something here where we basically look at the maximum peak and where it occurs. What you see is that when you include damping, the maximum peak does not actually occur at 1, which is weird. But damping shifts some things around. Again, this is something we didn't talk about in class. I'm going to say not to worry about this. Not worry. Don't worry. And then the phase, when it's undamped, the phase goes from 0 at R equals 1, it jumps up to 180 degrees. Right? That's because of that negative sign we talked about. This is when it was undamped, zeta 0, undamped. As we introduce damping, this behavior still exists, but not as abrupt. It's not just flat, up, flat. It's way more gradual. So what you'll see is that when we have low damping, it might look something like this. And as we increase the damping, it might have a more gradual transition. Do we see that? Again, think about the most extreme case. If we're undamped, perfectly in phase, perfectly out of phase. With the damper present, it'll cause that transition to not occur as abruptly. So we can see that here. That again, the undamped case would be what I'm drawing in red. Very poorly. forgot I could do fancy lines and notability. So 180 degrees is 3.14. Boom. So that red one that I just drew is the undamped case, that zeta is equal to 0. And then as the damping increases, you see that as we go this way, zeta gets bigger. The blue one here is 0.05, 0.1, 0.25, 0.05, etc. Because we are getting larger damping, we end up deviating away from that ideal behavior. The phase grows more, I don't say more quickly, I guess it is kind of growing more quickly in general. It's transitioning in a more gradual sense because the damper's presence is slowing the mass down, right? That's what it's doing. It's delaying it compared to the input force. So we end up introducing this phase difference between them. Is that okay? Hey, okay. Yeah. Charbel? Frankie. Yes, you could also do that because Q is related to zeta. And if you know what zeta is, you can determine what the transient, the exponential and the transient is. That makes sense? So if you have a high Q, that means you have low damping. So does your transient persist longer or shorter? It should be longer, right? Because zeta is small, you're not removing the energy as quickly. So therefore, the transient will persist for a longer amount of time. Audrey. What do you mean? That's just a big C. That's a big damper, right? So if you have a zeta of 0, that means that you're not dissipating any energy. The system just oscillates forever, even with initial conditions. We go back to note set 1 or 2, when we just had a spring and a mass, it would just go on forever, sinusoidally, with no input force. They just go back and forth. But once you introduce a zeta, that motion will begin to limit as time goes on and will decrease because of the damper removing energy from the system. Again, that's assuming free vibration. Once you have this force present, that is not going to decay as time goes on, but its amplitude will change because the amplitude of the position will depend on not just the force, but also the damping present in the system. But what this does is that it slows everything down. Like imagine I'm trying to run in still air versus in a hurricane. Like if the hurricane's pushing me back, I would like to go faster, but it's literally holding me back. So the force is saying in this situation, I want to go this way, but the damper says, no, we're not going that way. It slows it down. So it's not going to follow what the force wants it to do, which is what the definition of phase is, essentially. It delays it compared to the force. So when the force says go high, the mass is like, I want to go high, but I can't because this guy's holding me back. Okay, now I guess I'll go high. It's delayed a little bit. That's what theta is. Does that answer your question? Cool. Austin. Well, remember that at 1, it doesn't really exist, right? Because our amplitude is F naught over the differences of the frequencies, omega n squared minus omega squared. So at 1, it doesn't really exist. So right before 1, the phase is 0 because that amplitude is positive. Then right after 1, it's immediately negative. So we just represent that as this giant transition, right? Questions about this? Okay. And that's note set 8. Doubts about anything we talked about so far? Okay. Let's do note set 9 and then we'll take a break. So in this note set, I introduced 2 different ways of finding solutions to the differential equation that don't involve the gross matrices or anything along those lines. The first thing leverages Euler's equation, where we say that this cosine term is the real part and this sine term is the imaginary part. And what we'll do is, instead of using cosine here, because we try to solve the differential equation, it gets ugly. What we do instead is say that this is equal to F naught times what? E to the j omega t. Specifically, the real part of e to the j omega t. This is the real part of e to the j omega t. But it's very common to just drop that. Then at the end, you will take the real part of the answer when we're finding x of t. This we'll write as F naught e to the j omega t. Does that make sense so far? I just need to make, that's like the foundation of this note set. I need to make sure that that's okay. Now. Yes. Yes, what's the difference? You take the imaginary part, right? Now, in the homework, I just asked you to find the amplitude. At the end of that problem, you don't need to do anything with real and imaginary parts. You have to take the real or imaginary part when you're finding x of t, the total solution. Just the amplitude, you can do that. It's an easy way to do it, assuming the exponentials. You'll get the same answer as you would assuming x cosine omega t or whatever. But you don't actually have to take the real or imaginary part of the amplitude, because that's just a coefficient regardless. There is no complexity to that. Real plus j imaginary type of thing. But if you want to get back to your x of t, that requires finding the FRF, which has an e to the j theta in it. Now you'll start taking real and imaginary parts. We're going to go through that in a second. So if that's not 100% clear, don't stress. We're going to do it again. You okay? So what we do is assume that our x will be of the same form. Now, a thought you might have is we included a phase shift before. When we included a damper, we had x cosine omega t minus theta. Why don't I have something there? It ends up working out when we create the frequency response function. We end up including a theta there, so we do not need to include it here. Does that make sense what I just said? I see Austin taking his head yes. Kind of. Diella? Okay. Tracy? We're going to do that in a second. So we assume the solution, we take derivatives, the j omega comes down. We will plug that in. So here's the x double dot. There's the x dot. There's the x. All the exponentials cancel. And we can go ahead and solve for x. This is the amplitude in terms of all of our system components. The problem is, though, is that this is not a physical thing because of what? The j. It's imaginary, so that doesn't really make physical sense. So what we do is define the frequency response function, which is the definition of it is based on the output of the system to the input of the system. So the output of the system is x, while the input of the system is the force. That makes sense. The force is causing the motion. That's the input. The output is the amplitude. That's x. Is that okay? So once we solve for that, the definition of a frequency response function, we can represent it as the magnitude of this number. So the magnitude of that number, and then also the phase of that number. And that will be very helpful to us moving forward. That's the convenience of this method, is that once you have a relationship for the FRF, you can find the magnitude of it and the phase. And that's really nice and simple for us. Also note, I uploaded your homework that's due next week. I added one extra problem. It should take you like less than 5 minutes. It's finding the magnitude of a simple complex number. I'm asking you to do it in 2 ways. The 2 ways that we do it is with the complex conjugate, which again, I'm not giving you variables on that problem. It's numbers. It should be very quick. I think it took me a minute to do it yesterday. It should take you less than 5 minutes if I can do it in a minute. In theory. Do better. Yeah, do faster than me. Getting it right, though. So, one way of doing this is that you can multiply by the complex conjugate, because the definition of the magnitude, that's saying you have the magnitude of some number that's in this form. A complex number where the j is in the numerator. This is the square root of a squared plus b squared. That's the definition of it. If I have a j in the denominator, I can't do that as easily. So I have to get that j in the numerator somehow. And again, I taught you a trick to avoid doing this, but in general, you can't have a j in the denominator. So by multiplying by the complex conjugate, what you see down here, if you're looking at the denominator, is they have real times real. You'll have j real imaginary minus j real imaginary. Those go away. And then you have this term multiplied by this term, where the j's, what happens to them? They essentially cancel. J times j is what? -1. So that negative with this negative makes this whole thing positive. And the numerator, now we just have our typical complex number. Do you see that? So in this example here, this is the complex number with the j in the numerator, and I wrote it in terms of a real part and an imaginary part. Do we see how I did that? I separated the fraction. I just wrote this thing here as 2 separate fractions. K minus m omega squared over the denominator plus j times negative omega c over the denominator. 2 separate fractions, right? Okay? So now I'm in this form where I have the real part, the imaginary part, I can take the magnitude. That gets kind of messy, right? The algebra gets kind of gross when you do this, especially with variables. It gets kind of complicated. So what's the trick that we talked about? What's another way I can find the magnitude? The magnitude of the numerator divided by the magnitude of the denominator. We'll come look at this in a second, but simple way to calculate magnitude and phase. I have a whole section on it. If you have this as some numerator over a denominator, I can find the magnitude of the numerator on its own divided by the magnitude of the denominator. So as an example, I think, I'm trying to remember the homework problem. We can just literally do it. I don't remember the numbers though. I think it's 1 minus j3 over 2 plus 4j. What is that? 2 plus j4 over 1 minus j. Is that okay? 3j, thank you. This is a complex number I gave you in the homework, just to find the magnitude of. I'm not going to do the complex conjugate way. I want you to do that on your own. But in regards to this trick, we will take the magnitude of the numerator divided by the magnitude of the denominator. What's the magnitude of the numerator? The square root of the real part squared plus the imaginary part squared. What's the real part? What's the imaginary part? 16, right? So it's 4 squared. Same thing down here. It'll be 1 squared plus negative 3 squared. This will be the square root of 4 plus 16 is 20 over the square root of 10. That answers square root of 2. I told you. 20 seconds. I saved you 20 seconds on the homework. You're welcome. Thank you. What a guy. So, do we understand what I mean now when we say to take the magnitude of the numerator and the magnitude of the denominator? That's what that is saying. Now, if we come back to the phase is based on the imaginary part over the real part. That's the definition of phase. And a way to justify that is by drawing it in the complex plane. So in this example, I'm plotting 3 plus 4j. That's a complex number. If I plot it in the S-plane, for example, where you have the real axis and the imaginary axis, or the imaginary plane, complex plane, whatever you want to call it. This is the real part, the 3. We'll travel 3 to the right. And the imaginary part is 4. We'll travel 4 up. The magnitude is the hypotenuse of that right triangle. By Pythagorean theorem, that ends up being the square root of 3 squared plus 4 squared. That's where that comes from. Is that okay? The phase is the angle that this makes with the x-axis. So we find that by doing the arctangent of 4 over 3, which is the same as the arctangent of the imaginary part over the real part. Do we see that? Is that okay? Doubts? Okay. So the faster way to do it is to do what with the phases? We have a numerator and denominator. Instead of doing the whole complex conjugate thing to get it in that a plus jb form, how can I find the phase using the numerator and denominator? It's a difference between the angles. You subtract them. So again, if we do the same problem or something similar, let's say we do, I think we'll do the same thing. I don't ask you this in the homework. Let's just say it's something like this. This will be the arctangent of 4 over 2, the imaginary part over the real part, minus the arctangent of the imaginary part over the real part. So that's the same as the arctangent of 2 minus the arctangent of negative 3. Is that okay? Without a calculator, what's the arctangent of 2? No, I'm kidding. You guys can't. I can't do that either. No, you could do the phase thing, but you should. I expect you to know your common 0, pi over 2, pi, like the 4 things on the unit circle. I expect you to know how to do. Again, that goes back to high school, maybe middle school for the extra smart people. So it should be in radians. Don't worry about it. You don't have a calculator in your exam. So that's how you do that. If you go through that stuff, you end up getting the answer for the magnitude and the phase. Now that we have the magnitude and phase, we go ahead and write our frequency response function. Here's our magnitude, here's our phase. Our frequency response function in general is output over input. That's the magnitude over e to the j theta. So I have here this is the magnitude, and this is the phase, e to the j theta. I ended up reducing it and multiplying both sides by f naught to find the amplitude, but that's fine. Then once I have this, because remember I found theta, I have all the variables I need, I can say what x is. X is equal to this thing multiplied by f naught. That's what I just had here. That is the amplitude. Based on our original definition of x of p, the particular solution, we have x times e to the j omega t, where this whole thing is x. We plug that in. The way I do this in the notes is backwards. It's right, but it's stupid. I'm going to fix it. I don't know what I was thinking last year. But this will be equal to this whole thing times e to the j theta, e to the j omega t. Yes. Yeah. How I'm feeling. I wanted to mirror that, you know. So many smiling faces here, Peter.
How do you find? How do you find happiness? How do you find spirit of happiness?
Just look at me. So happy. You want the spirit of happiness? I'm right here. So what?
Because we had a whole Arctic party yesterday, and I found out you were in a frat.
Oh my God.
Who would have thought?
I know. Surprising.
Where you were?
High five. I was not the president. I was the new member educator, though. That's what kind of motivated me to go to academia ultimately. Yeah. Kegs by myself? You know I have a stomach problem.
Yeah,
Exactly. So, back to reality. Even though that kind of was reality. That's an old reality. Mom's spaghetti. Oh, yeah, got it. So, I'm going to ignore this. I'll fix this. But what you do now is that you have this amplitude times e to the j omega t plus theta. Right? We can multiply those exponentials together. You add the exponents. Did you find a picture of me?
I drew for that.
Did you actually?
This is so blurry, though.
So, all right. We can make fun of this later. I want to get through the note set so we have time to review. So, once we do that, we have this f naught over the square root thing. Evil smiley face. I know it's evil. Evil. So, this is your particular solution. This amplitude multiplied by e to the j omega t plus theta. This is not a physical thing because of the j. But what do we do to get it physical? We take the real part of this number. Matt, that's what I was telling you before. This is the answer. We have to take the real part of this to get back a physical thing. So the real part of this will be what? This is real, so that just chills. Cosine, exactly, based on Euler. This thing here is cosine omega t plus theta. Therefore, the real part is cosine omega t plus theta. And then we end up with our final particular solution where I plug in theta. And again, it ends up mathematically being negative, which makes sense because we expect a delay. We expect the graph to move to the right because of the delay due to the damper. Yes. This specific thing, probably not, but this and this individually are on the formula sheet. So you have to know like where they go, but I do give you those equations in general. I almost done with the formula sheet. I started it last night. I'll post it soon. Is that okay? Doubts about the complex response method? Yes. Yes, that's literally all that happens with the particular solution. Is that okay? We talked about this already. You had an example in your homework. I go through this in class. The other method was a transfer function method. You have a problem in your homework that is due next week that involves this. But the general idea is that if you take the Laplace transform of both sides, I will give you these Laplace transforms, at least the ones you'll need for the exam. We will see a lot more of this on exam 3, Laplace transforms, but for now, we're just going to limit it to a few of these. But what you'll do is you'll take the Laplace of both sides. And again, I give you the tables for what the Laplace of each of those terms are. And you end up with something in terms of Laplace variables, where you have these S's. The Laplace transform of x of t is x of s. And we'll do the same thing like we did for the frequency response function. We'll solve for output over input. And that will give us this transfer function. Okay? Yes. Possibly, yes. Yeah. Yeah. Let's just say that this will be the heart of exam 3. Yeah. It will be the same. It'll still work out the same. So this is basically, if you plug in what S is j omega, you get the same exact thing we got with the complex response method. It ends up being identical. And in your homework, you have a problem where you'll actually do the inverse Laplace transform. Again, it's just tables. I actually give you hints in the problem statement how to do it. It's very easy. But that's the end of note set 9. Questions about note set 9? Okay, let's take like a 5-minute break. I know it's usually 10, but like I want to get through all the note sets for your benefit. So let's take a 5-minute break or so, then we'll come back. You want to see a funnier picture? I don't think what they just like I prefer B. I was unbanked.
Oh, right. Vice president. Figured president.
These are all I need to know. Meathead. Did I? These are like the meathead guys and stuff. And you have
In the front. Like, half the time.
simple.
How old are you? That's a good point. I was gonna say. That's
20.
okay.
They're just 4 times my size.
In every direction.
Literally every direction.
Wait, how do you look that up? Just type in.
I typed in UFIFC, standard fraternity council, then my name, then it pops up. Oh man, brutal. There it's good. Yeah.
I think you said this before. The volume vector, they invented that
It's not so much they did it for that, but like that's the way they characterize it. So if you like, see if I can find one.
Because the purpose of maximizing is to minimize it.
Yes. So like if you look, let's say on like Google Scholar, resonators. I'm just gonna like click. The temperature depends on the quality factor of MEMS resonator. That's literally the title of the paper. Like it's very important for MEMS. Yeah. The temperature dependence of the quality factor of MEMS resonators is analyzed and measured. So I'm sure they have a graph that's like showing you the frequency response or something. They typically do. But they're just showing you how the quality factor changes as a function of temperature. This is what people research though, you know? Let's click this random one. Note the quality factor is defined in a linear sense. Q is equal to this. That's 1 over 2 zeta, basically. They only have 2 references in this. But basically, anytime you see a MEMS resonator paper, that is like what they talk about. Accurate modeling of quality factor, everything's quality factor. Very important for the field of MEMS, especially the resonators. Because when you want to have a resonator, you don't want it to be damped. You want a high Q. You want a high peak as possible in resonance. You got something that oscillates for a while without losing energy. You don't need to constantly supply it energy. It's a way to save energy from an external thing.
You say the,
Yes. Yeah, like we look to love down the model. We can relate mechanical systems to electrical and vice versa. Yeah. You can do the same thing with electromagnetic waves. That's maybe in the electrical department, not mechanical. Maybe the electrical, maybe the physics. Things like that. Yeah, I don't know if they would model this stuff in those classes. I feel like it's rare in electrical class to bring springs into it. You know what I mean? Yeah. 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 I don't know.
You should put another word on.
Third one.
Yeah.
You guys should also put work orders in.
We should just stand really tight together in a circle. On the transcript, you don't say it. It's on the transcript. You're the next. You're young. You're him.
Oh!
You know, Miguel's only like 4 years older than me.
Exactly.
Really?
I'm like 5, I think. He's like 36.
He looks 20 years.
Okay, let's get back to it. We're done with our break. 2 more note sets. Then we can look at the old exam, which really doesn't have that much of this material on it, unfortunately, because I didn't do 3 exams last year. I basically did the equivalent of your first exam and what will be your 3rd exam. The 2nd exam material was very minimal, which is why this exam is going to be difficult for me to write, because it's all kind of the same thing, you know, just in different forms. Base excitation. Where we have a base that is moving. We say that the motion of the base is given by y of t. And that movement of the base will end up impacting the movement of a mass, which is moving at x of t. So from a relationship perspective, stop distracting other students and take the single thing. So from comparing this to, let's say, note set 8, what is this base represented as? If we think back to note set 8. It's the force, right? This is what's going to be exciting the system. We only care about the mass in motion, but this external thing is providing a force to the mass that causes it to deflect. And again, in real life, you don't see this. You don't see like a base attached with a spring and a damper to a big mass, but we represent things using this model, which is why it's important. Yes. Really? I didn't see that. Okay, so for some art installations, that is a thing. That's pretty cool. So we have some examples of that. We talked about a car driving over a bumpy road. We did that example yesterday. I mentioned sensors have something that's moving inside the sensor, and as something you're measuring is moving around like an airplane wing, it causes the little mass inside of the sensor to move. That's a base excitation problem. So we do see this in different instances in life. All right, let's take a 20-minute break. So the way that we derived this ultimately was noting that when the base is brought upwards, so if we assume the mass is hanging out, and then the base is brought upwards, let's say to here, so it's gone up, what direction is the force acting that the mass feels? The mass is going to want to go up because the spring does not like being compressed. It's going to try to push out in both directions. So the base will feel a force going down, but we don't care about that. The mass will feel a force going up. And that's based on ky, which is why in this picture we have kx minus ky, because I drew it going down. It's the opposite. Because it's going up, I write it as a negative if I draw the vector is going down. Does that make sense? Not because it's not because the base wants to go down. It's that the spring wants to go back to equilibrium. And in doing so, it'll push the base down and push the mass up. Those two things are happening simultaneously. But we only care about what the mass is experiencing, which is that spring force that's pointing upwards. Is that okay? Doubts about this? Same thing with the damper. The damper is the same thing. It acts just like the spring. The only difference is it's based on velocity and not position. Is that okay? Feeling good? Okay. So we say that the base moves at some y sine of t, sine of omega t, where that omega is the driving frequency of the base. And so So we'll do something very similar to the past. We'll either take derivatives of this and substitute it in, or do the complex response method where we say that this is y times the imaginary part of e to the j omega t. And you can go through and end up solving this. We see that we end up with two inputs in this differential equation. This is from the damper, and this is from the spring, because you have the K and the C. So because of both those things present, we end up with two different forces that are happening at the same time. The long way we did it in class was we did superposition, which is where we assume that the system is linear, meaning we can add the total responses together. So we would find the solution to just this is the input by itself, store that somewhere. Then we find this position with respect to that external force and store that somewhere. Then at the end of the day, add them together. And that gave us our total solution due to the base moving up and down. That makes sense. That's what superposition is, this idea of looking at individual things and then ultimately adding them together. So we did this in general. We used our same answers from note set 8. These are the formulas we just showed before for the magnitude and the phase that we found in different ways. The crappy matrix way, which I skipped over, which you don't need to study, and the complex response method, which you do need to study. So you end up with two particular solutions. I'm going to skip over all of this because we did it in class and it's kind of tedious and algebraic. But what you get ultimately, that's the second solution. When you add them both together, you end up with this obnoxious function. But the thing that we care about the most is this thing. What is this called? That is a transfer function, but specifically for base excitation. What is this name? It's the displacement, which is not that long. Transmissibility. Yeah. This is the displacement. Transmissibility. It's basically saying how much of y's motion is transmitted to the mass's motion. How much of the displacement of one is being transmitted to the other. That's what displacement transmissibility means. I do some algebra here to rewrite this in terms of the damping ratio and the frequency ratio. So we see that in this specific kind of system, we end up with the displacement transmissibility based on R and based on zeta. I won't expect you to derive and do the algebra. Again, that's a waste of time, I feel like. But what we see is how this changes as a function of frequency. Again, as we have more damping, we have less deflection in general at resonance, right? When R is equal to 1, we see that we're taking energy out of the system with more damping. Therefore, the current doesn't go as high. 0.7, low Q or high Q? Low Q. I just wrote before big Q, big P. Right? This is low P. That's big P. Low Q, big Q. Okay? So, we do see that as we approach resonance, we do have greater deflection compared to other frequencies. Again, that makes sense. We're exciting the system at its happy spot. We see that when it's very low damping, it goes very high. If we look at this graph, another thing we can pick out, like let's just say we look at this point here at resonance. let's say that's approximately 5, the displacement transmissibility. So if the base is moving at an amplitude of 2, what is the amplitude of x? 10. We multiply, right? If I say x over y is equal to 10, I know that x is equal, or not to 10, sorry. X over y is equal to 5. X is equal to 5 times y. So if the amplitude of y is 2, then the amplitude of x will be 10. That makes sense? So just this little amplitude of 2 will cause a great amplitude of 10 at resonance for that specific damping situation. Does that make sense? Cool. We also talked about this very specific location where no matter the damping, there will be a ratio of 1, x over y, meaning that when the base moves up by 4, the mass will move up by 4. It ends up being exactly equal. And at that location to the right, we have something called the isolation zone, meaning that the mass really isn't moving anymore. It's moving less than any sort of deflection that is occurring from the base. Again, that kind of mirrors what we talked about in the past with our input force. If the frequency is really high, we'll have some sort of decrease in deflection because the mass does not have time to respond. Does that make sense? Is that okay? Okay. So I go through some stuff here, conceptual stuff that I want you to read. I also do an alternative derivation in the notes where we do the complex response method, where we say that y of t is equal to y e to the j omega t. This is exactly the same thing we did before in note set 9. We'll take derivatives. We end up assuming that we know that this is the assumption of y. Our x will be of the same form. We'll plug all those derivatives into this expression and solve for displacement transmissibility, x over y. And we end up getting this relationship here. How do I end up with the square root function I just showed you? It's the complex number. How do I do that? Yeah, I got to take the magnitude of this number. Take the magnitude of the numerator, the magnitude of the denominator, and divide. That will give me, ultimately, the same exact relationship that we had after doing the superposition solve two differential equation technique. This is technically faster. It doesn't require as much thinking. You don't need to worry about doing two different differential equations and all this math. You just plug in e to the j omega t essentially with the respective amplitudes, take derivatives, and go. And then you get your answer. Do we see that? Questions about that? Lonnie? You okay? Cameron? It's okay? Okay. Do the same thing with the phase. Again, a lot of algebra. Kind of similar to what we saw in the past. A little bit different is that we see that if it was an undamped type of system, again, we would have this behavior where it goes from 0 to 180. Right, that's the same type of thing ultimately for an undamped system. But depending on the damping, again, that impacts how well that models the undamped case. So we see that when we're at 0.05, which is the blue curve, which is this curve here, that's 0.05. It's pretty close to modeling that. But as you increase in damper, specifically like the green curve, where this is critically damped, it's very gradual. It doesn't even go near the 180. Again, that's just more of a mathematical conclusion from that. Yes.
Go to 180 because see them like sloping down.
Yeah, yeah. They won't. No. I was trying to like correct myself when I was saying this. This won't go exactly 180. It will level off. There's a limit. So if you were to look at that phase equation and take the limit for different R's, because the face is this weird thing here, you end up having different phases depending on what zeta is. So if R goes to infinity, you'll have an R in the numerator, and you'll have a zeta in the denominator at the end of the day. So you have these two things that are both occurring. So the phase is a little bit more complicated for base excitation. Again, because it's a lot different, I'm not going to probably ask. I don't think I'm going to ask you questions. The phase questions will come from notes at 7 and 8. So that's like the heart of this test. These are applications of those things with minor variations. Okay. That's note set 10. That's base excitation. Is that okay? Okay, one more note set. 11. Good. Yes, I will. But the problem is on there, there's only like one problem that relates to your exam, which is why it's like, I don't even know if it's, I'll tell you what that problem was. It's based on rotating unbalance. I'm sorry. But we'll look at exam 1 again and answer the questions on there. Yes. Yes, you can fully complete it now. Yes. We can look at that after we're done with this. So, rotating unbalance. We had the demoing class that I brought in where we saw this thing spin because we added this unbalanced mass to the system. The rotation of that mass is what is causing the crazy vibrations of the overall system. We see here that we have in this picture this mass that is rotating in a circle. Because this is rotating in a circle, it causes this force to be acting on the rest of the system, basically causing it to move up and down. So as this mass goes down, imagine that this force is going to be causing it to go back down as well. Some heavy dot is just causing this thing to go like this, right? As it goes up and goes down, it just goes ahead and goes up and down with it. That makes sense? That's what's physically happening. But of course, as the frequency changes and stuff, we end up with weirdness that happens, like we've always seen, where the phases change and the amplitude changes. But that's the main concept. You have this thing rotating, causing this force. Is that okay? So, to derive this, we had to do two sets of Newton's law, F equals ma. We looked at the rest of the system, which does not include the mass. So we assume that this was going up x of t. We had kx and ky going, or not kx, kx and cx dot going down. What other thing am I missing here? Yeah, the force from the rotating mass that's going to cause it to go up. So this is m minus m naught. We're just looking at the system being affected by the point mass. Then if I look at the point mass itself, the only force that's acting on it is the equal and opposite force of the rotation. So you end up with this force going down. In regards to its position, what is its position? We'll deal with that specifically in a second in a general sense. What two things are contributing to its position? Well, sure, that's the rotational part, right? Yeah, it's based on the angle. What's the other thing that also deals with the position of the mass, the point mass? Well, that's related, right? Oh, that's all rotation. The overall position of the mass, the big mass. Because remember, this thing is moving up and down. This is rotating inside. Like imagine here's my hand. I'm rotating it. Its position is dictated just by the rotation. Now imagine that I'm moving up and down also, right? My hand is moving with me. Yes, I'm getting my workout in. So, so you can see that this is based on two different motions. It's rotation, then also it's translation. I know I'm not doing this really great. I'm not going to be a perfect circle. But this is based on both the up and down movement of the mass and its own rotation. So this is based on x of t plus x rotation of t. Does that make sense? Both those things are happening simultaneously. So we do F equals ma on the left one and F equals ma on the right one. So this is the one on the left, the big one. We have our three forces, the rotation force, the spring, and the damper, where we assume the positive direction that X's force is causing it to go in that direction, and the spring and the damper are acting opposite the motion. And the mass of that is based on total mass of the system, not including the point mass, n minus m naught. Is that okay? Okay. Times x double dot, that's its motion. It's just based on x. There's no x rotation there because this big mass is not rotating. It's just going up and down. So in order to find out what this is, we'll look at the free body diagram of the other mass, where we see that the only thing acting again is that rotational force in the equal and opposite direction. So we'll say that the sum of forces on this, which is minus FR, is equal to that mass times its acceleration, which is based on the translational acceleration and its own rotation. That's the derivative of the x of t I just wrote before. Xt plus x rotation of t. You okay? So x rotation, this is based on the eccentricity and the angle. We say that x rotation, or xr, that is this distance here. I'll try to draw it in a different color. That is this distance here. What is that going to be? E sine of the angle, which again, we're writing that angle as omega r times t. Omega is radians per second times seconds gives us just radians. That's the angle at a certain point in time. So we can take derivatives of this. Here. And we can plug that into our differential equation. Basically, we find out what the rotational force is. We'll plug that into the other one. And a lot of things cancel. And then we end up with a differential equation that's just in terms of the total mass on the left side, which is the same thing we've seen in this class every time. The only difference is now we have a different forcing function. Well, a different F naught that's based on this specific situation. So this is F naught. See that? Is that okay? Okay. So let's look at this. If the mass is large, then the force it creates is greater. When I say the mass, I'm referring to the point mass. If the mass is further away, that force will be greater. Again, remember, if it's really close to the center, it's not rotating. It's not causing a rotation in the mass, the overall system. That won't cause any up and down movement. If it's just in one spot, there's not going to be any additional vibration caused by this being present. That makes sense? So we see that E plays a role, and then of course how fast it's moving will play a role in the force. But as we've shown, this might impact the force, but in regard to the x of t, omega r, will have a big impact in regards to how the deflection changes as omega gets bigger. We'll see that it ends up decreasing as we go past resonance. Anything I say that confused anybody? That's saying no. Jacob? Sorry. That was, oh yeah, by the way, I think I need one more person to fill out an evaluation. Has everybody in the room filled it out? Yeah, you fill it out? Okay. I think we're like at like 73%. Go blow up the Discord and get somebody to do it. The reason I ask is that somebody complained, like, I know this isn't your fault, but the room is really cold. I'm like, I know. I've tried to report it, guys. I'm sorry. I can't fix this. Maybe I should ask Pirtle. He can fix it. I'm going to ask Frank if he can fix it. So, we could go through solving this differential equation again. We could do the same type of thing we did in the past. We can find, we take the imaginary part of it because our forcing function is sine. And we can go through the same type of thing we did last time. I just redo this math in the same exact way. It's all matches up. So our final response depends on the point mass, the big mass, the eccentricity, the frequency ratio, and the damping. I hope that all makes sense why it depends on those things. We have more damping, that'll change the response. If you're oscillating near, at, or above resonance, that will change the response. If you change the size of the point mass and where it is, that will obviously change the response. All these things play a role. If the mass of the system gets larger, the impact of the little mass gets smaller. It's a relative thing. If I have a fly on my machine versus a baseball on my machine, it will have a different impact on the response. Does that make sense? What? You making fun of the Mets?
No.
Oh, you're flying your baseball, then you're, I guess, double screwed. So we see again the same type of relationship where as we approach resonance, the response gets larger. But what's interesting about a rotating unbalance is that the deflection does not go to zero as you go to higher frequencies. It goes to a normalized magnitude of 1. So if you were to take the limit of this as r goes to infinity, we'd have an r squared on the top, and ultimately in the denominator, we'd also have an r squared with the limit. This is r to the 4th. That's too small, we don't care about it. The 1's too small, we don't care about it. Square root of r to the 4th is r squared. It ends up not playing a role anymore. It's just going to be equal to the deflection, this. So we'll still have an impact. It won't go to 0 because the mass, the point mass is moving around. And we talk about how the mass is not time to respond. Well, depending on how big this mass is moving, it will cause the thing to respond. It's kind of a little bit backwards than what we see. The mass has enough time to move, but in this problem, a mass is the forcing function, basically. That's the thing that's causing the motion. So it ends up being a little bit different. Where we see it doesn't go to 0 as time goes to infinity, or as r goes to infinity. It goes to just this value. Is that okay? And again, same deal. Whereas we increase in frequency, our phase approaches 180. And then beforehand, it is supposed to be close to 0. And again, as we deviate from the ideal, we end up going to this more gradual transition as opposed to this abrupt transition that happens. Questions about this? Concerns? Okay. That's note set 11. Let me pull up the exam from last year and look at the questions we skipped. If a force vibration system has no transient response, what does that imply about the initial state of the system? No initial conditions. The transient is only related to the initial condition. So if X naught and V naught are 0, there's no transient. So the answer to this is no initial conditions, or X naught is 0 and V naught is 0. Does that make sense? Remember, steady state is based on the force. Transient is based on initial conditions. If there's no initial conditions, there's no transient. That's it. Doubts about that? Yes. That's the homogeneous. Yeah. Yes. It's being pulled back and forth at some frequency. And again, we saw that the natural frequency doesn't have a role on that, but that does not, that's a still steady state. That doesn't go away or die out, right? So if you have a transient response, that means it's based on an X naught and V naught that are non-zero. No transient response, initial conditions must have been 0. There's no free vibration problem. It's all forced. Is that okay? A spring mass system has a natural frequency of 10 radians per second. It is being driven by an external force at a frequency of 8. What is the frequency or the phase difference between the force and the mass? So go ahead. Why don't you take a second to think about this? Give you 2 minutes. Remember, it's spring mass. It's not spring mass damper. Damper would make this problem impossible to do without a calculator. But without a calculator and in the spring mass system, you should be able to do it quickly. That's what I know. Does anybody get it right away? He's missing this because he went to Boston to celebrate a parade. Now he's missing out on quality stuff. Okay, somebody explain to me what I'm getting at in this problem. What is this problem testing you on? Did you get a revelation? Spring mass system. Tracy, did you get it? Okay. Let's talk about what we learned in note set 7 with phase. If our amplitude that's our amplitude of the system, right? It's this times cosine omega t. Without a damper, our phase is either one of 2 things, 0 or 180. When is it 0? Less than 1. Debate, fight, go. Why is it 0? R. Yeah, the graph of your phase, that's the graph of your phase. When you're less than 1, R is equal to 1. When you're less than that, that means that this amplitude is positive, which means that your mass and your force are perfectly in phase. Does that make sense? I need to know, because it sounded like it made sense when I was going over note set 7, but I don't think it clicked. Because remember, x of t is x cosine omega t. The force is f naught cosine omega t. If x is positive, which occurs when omega n is greater than omega, then this is just some cosine function that's in phase with this cosine function. They're in phase. The phase difference is 0. The answer to this is 0 degrees. If x were negative, meaning omega n is less than omega, then this would be negative cosine, which would be 180 degree phase shifts. So this is 0 degrees. Okay. Yeah. But I don't want you to, yes, you would. But I don't want you to just fucking guess 0 degrees. I don't want the 50-50 thing to be in your head.
I know. I got 50-50. It's better than multiple choice.
Maybe I'll make it multiple choice. I'll say 0, 52, 71, and 180. Now you got a 25% chance. Not everybody knows that. So, if a damper was included, would the phase become greater than, less than, or equal to your answer from part A? Assume that all the phases are positive. Okay, prove to me why. That's a 1/3 of a guess. Why is it greater than? I'm going to tell you you're correct. Dylan. There is a phase, so it's not equal. So let's go back to note set 8. You need to know these graphs. Pretend it's thermal systems for a second. You have a million cycles to know all the graphs to memorize. Yeah, he doesn't tell you what they are, though. He just gives them. Not giving you shit. Take off the axes. Yeah, I'm not gonna do that. So when it's ideal, it's 0. When it's ideal, it's 0. As soon as you add a damper, it delays things. So that means that it has to be greater than. If the answer was 180, the phase will be less than, because it doesn't reach 180. It's the non-ideal case. When you don't have a damper, it's 0 or 180. If you have a damper, it's in between. Does that make sense? The damper slows things down. It introduces a phase. So because it introduces a phase, it will not match the ideal case that is undamped. Does that make sense? Thank you. That's when you have probably free vibrations, what I was talking about. That's I don't know. I don't remember. So in this one, this would be greater than. Because again, the ideal case is this one. If I introduce a damper, it'll do something more like this. Quality factor. For a spring mass damper system, that the mass and the damper values are held constant and the stiffness is increased, what happens to the quality factor? Take 2 minutes to try this. What's the definition of Q? 1/2 zeta. It says the mass and the damper are held constant, but the stiffness is increased. So K goes up. We have to remember what the definition of zeta is. Again, when I say remember, I mean go look at the formula sheet. Zeta is C over C critical to square root of Km. So if K increases, what happens to zeta? Zeta decreases. then Q increases. Now, if you know the definition, what the variables are, this shouldn't be a difficult problem, right? Like, some people on the last test confuse like what damping coefficient and damping ratio are. Like that type of thing is that's a mistake you should not make. Because a lot of times I ask you again are kind of conceptual. You have to know what is what in order to solve the problem. What I would recommend, I'm going to post the formula sheet today or tomorrow. Go look at the formula sheet carefully. Ask yourself, what does this equation mean? I break it up into sections, but I don't tell you the words. You need to understand what variables go into what equation and why. What happens if I don't include a damper? Oh, it'll reduce to this. What happens if I do this instead? It'll change to this. Like, I need you to envision those types of questions in your head when you're looking at that formula sheet. Because on the last test, I said derive this. People derived a bunch of random stuff. And I'm thinking, how did they get this answer when the real answer is on the equation sheet? Like if I'm taking the test and I don't get what's on the equation sheet, that means that I've messed up. A lot of the times your answers will be on the equation sheet in regards to derivations, at least. You just have to know how to derive it. Check the equation sheet, make sure it makes sense. Go look at it. Don't wait till the day of the test to be like, oh, we get an equation sheet. Cool. Look at this. Like, don't do that. That's pretty nice that we're given that, but you have to go ahead and prepare. Is that fair? Does that make sense? I'm trying to, I technically do not need to give a formula sheet. You could derive everything if I really wanted to be an asshole. I'm not. I'm giving you a formula sheet, but I guarantee there's some professor somewhere that wouldn't. So, extra credit. Circle either increases or decreases for each question. What happens to the rotating response or vibration response of a rotating unbalance if the unbalanced mass gets larger? That increases. The unbalanced mass moves closer to the center. I heard in. It gets closer to the center. Decreases. More mass is added and equally distributed to the system. That decreases. That's M going up. Is that okay? The first question on this test was draw a free body diagram of the mass, including proper forces and vectors going correctly. So again, based on this, we draw a mass. This is base excitation. The only thing that it feels is the spring and the damper. What's the spring force? Kx minus y. What's the damper? Minus y dot. I said to derive the differential equation. Don't solve it. Just derive it. So sum of forces is equal to mx double dot. If I'm assuming that this is the positive x direction, which I give you in the picture, it's going to be negative kx minus y minus c x dot minus y dot is equal to mx double dot. Negative kx plus ky, that's subtracting minus cx dot plus cy dot is equal to mx double dot. We'll bring all the x things to one side. And then we get our typical differential equation, where we have two forcing functions, ky and cy dot. The amount of people who got this wrong, that was the end of the question. That's it. It was like a 50% this question. And I was like, know how to derive this. And only half the class learned how to derive this. Do not be like them. Do not be slackers. Study this. Yes.
So a lot of derivations come from some forces and some motion.
Yes. That's No, because I can ask you, here's the differential equation, derive the frequency response function. Find the magnitude in the phase, that type of thing, right? Yes. No, not at all. That's fine. But the thing is, though, like, the issue with making it monic is that you might make algebra errors by dividing by n. You technically could say k over m and c over m, but if you were to substitute in omega n squared, 2 zeta, like, you just might make a careless mistake somewhere that would get points off. But this is good enough. This is easy. Is that okay, Tarbell? You're giving me good ideas. So that's all the stuff. I think on the other exam, I asked, like, if I had a rotating unbalanced system, and the only thing you're allowed to change is the angular frequency of the mass, the speed of the motor. That's the only thing you're allowed to change on the inside. Can I do something else besides decrease the speed to lower the amplitude? You can increase it. A lot of people got that wrong. But that was the only other question I asked from this type of stuff on that other exam. So, like, I'm not going to post that exam. I'll post it later because I don't want to overwhelm you. I could just post the one question again. Sure. Of what? Oh, do you fill it out? Tonight? Let's see. 38, we did it. Oh, you can't see it. 38. 38 people. 80%. Yay. 47. 38 out of 47. 50. So there was a few people that dropped for, like, not, like, difficulty reasons. Like, I know Jester dropped, but he had to take heat transfer. Moro dropped because he had Jesus Christ. Moro dropped because he got an internship, full-time internship, and I think somebody else dropped for some other reason. But, like, they weren't like, I'm afraid of freakets. You know, you guys were the ones that overcame your fears with taking this class. Any questions about anything? If you want me to make a video on something, let me know. I'll do that this weekend or next week. If you want me to do an example problem, let me know. We didn't have time to do that today. I wanted to go through all the notes that's in the exam. Please reach out to me if you have questions. Okay, cool.